All right, guys. So I just want to talk today about confidence intervals. That was one of the things that I think we didn't get a chance to go over for the exam review, and it's also part of homework 3. So I'll do it in two parts. We'll do a general overview of confidence intervals here in the beginning, and then we'll actually address like more specifically what homework 3 is talking about. And they're both kind of good to know. Homework 3 is just kind of a more specific um, example of what confidence intervals are, um, and kind of showing it with data, and you'll see what I'm talking about when we actually go through it. But anyway, this will be the first part of the kind of two video series. This is just the general one, and then the other part will be on homework 3. So anyway, let's hop into it. Confidence intervals are basically an assertion of how confident you are that the true population mean uh, falls between the said interval for your sample. And this is important because a lot of times, especially in statistics, we don't have the full population. We don't have access to the data about it. We can't um, we can't know what all the data points are in the population, so we have to take a smaller sample and try to estimate things about the true population, or the whole population. So, for example, if we wanted to know um, the the weight of every rabbit on the planet, to know for certain what the mean was, we would have to actually take the weight of every rabbit on the planet, and obviously we can't do that. So we take a smaller sample, and then we estimate what the true mean of the population is, and then the confidence interval is a way to gauge how certain are we that the true population lies on, or lies in the confidence interval we have for this smaller sample. Where was I? Okay, so now that we have kind of touched on what a confidence interval is, um, let's kind of go over the basic shape. So this 95% confidence interval basically says that for 95% of the area under the curve, we're going to draw 2 points. Okay, and we are 95% confident that the mean, or the population mean, lies somewhere between whatever this value is and whatever this value is. And this essentially is kind of like the z-score of like 2% of the area, or 2.5% of the area. And that will give you this lower bound, and then also the z-score of 0.95%, or 95, sorry. So 95 plus 2.5, so 97.5. Yeah, that's right. 97.5% of the area will give you this upper bound. And in between these two bounds lives the confidence interval. So that's kind of a synopsis of really what confidence intervals are. And then to actually create them, we use this formula, or this is a very general formula for confidence intervals. So we have the z value, which is the confidence level value, which essentially is the z score corresponding to the confidence level that you want. So for 95%, it's 1.96. That's going to be positive 1.96 and negative 1.96. And in between those two values is going to give you 95% of the area. Right, so, and then we need the sample standard deviation, and we need the sample size. And so it's this z-score, or this confidence level value, times the sample standard deviation over the square root of the sample size. And then that's going to be plus or minus the mean, the sample mean. And if you think about it, that's going to give us our lower bound and our upper bound. Okay. So common confidence level values. These are common because they're used a lot. So people will say 80%, 90%, 95, 98, 99. These are all normal confidence interval, or confidence levels that we use. So we have a z value associated. So for example, I said 95 before, and that corresponds to 1.96. So that's just some common ones I put up. You can also calculate them yourselves. It just really depends on what your applications are, but typically you won't need any other ones than these. Let's get into code now. So this is going to be a general way in Python just to calculate confidence intervals. And so we're going to need NumPy, we're going to need matplotlib. This is just to kind of illustrate things. But first what we want to do is we want to generate a data set of 1,000 values from a normally distributed population. So we're going to say that of this, maybe we know the population of rabbits somehow on the planet. There was a mean weight of 10 pounds with a standard deviation of 2 pounds. Let's just say. And now, from that population of rabbits that we know is distributed in this way, with a mean and a standard deviation of this, we're going to take 10,000 rabbits for our sample. And just an interesting illustration. So if I change this to, you got kind of a nice bell curve shape right here. But if I change this to 100, it looks horrible. If I change this to 1,000, it looks slightly better. And if I change this to 10,000, it looks like it should. Just, interesting to show that the large sample size really does have an impact on these things. But yeah, so we now have our sample. We have 10,000, just call it rabbits. And now we need to find the number of samples, which, we already said was 10,000, but say we didn't know. We have to count all the samples. We find our sample size, call it n. And we can use NumPy to find the mean, and then find the standard deviation. And I'm not really, we could calculate them by hand, but I'm not really going to go to that level of detail. If you really need to know those things, you can just always find it online. The z-score we talked about, so in the table above, we know that 95%, the z-score or the confidence level or whatever you want to call it, corresponds to 1.96. And then we can use that to calculate the interval half width, which in this is this part of the equation. And that's, again, the z-score times the sample standard deviation over the square root of the sample size. And then finally, we just want to add or subtract and add those from the mean, the sample mean, to get our start of our interval and the end of our interval. And then finally, we can print the confidence interval here. So as we can see, we're really confident that our rabbit, or that the population mean, is going to be in this these ranges, which is a really small range. So we're very confident that the population mean is going to be in our confidence interval, and our confidence interval is very small. So, and the reason why that is we have a lot of data. So if I change this to, just for the sake, we'll change it to 100, and then we'll redo all of these things. And now this confidence interval just got a lot bigger. Not significantly, but a lot bigger than what it was. So just some interesting things to play around with. And now this is just two other ways I found to quickly calculate the standard deviation. This is just code I pulled off the web, and I liked it. So this is just, maybe easier depending on what your application is for the exam, but you're gonna need SIPI for this. But anyway, so we're gonna start with some random data set. We're gonna specify our confidence level, and this is the part I liked about this, is that you could specify any confidence level. So you could specify 96 point or like 0.96752, and it would all go through and basically calculate the z-score for you and do all of these calculations you don't have to worry about. So I thought that was neat. Anyway, we're gonna need the degrees of freedom, and that's because we're actually using the t distribution. which we'll talk about a little bit later in homework 3. But essentially, the t-distribution is what we use when we have a very small sample size of less than 30. And we'll get into that a little bit more in homework 3. But so anyway, we specify the confidence interval, the degrees of freedom, which is just the sample size minus 1. And then we calculate the sample mean. And then in this time, we're going to calculate the sample standard error. So this is one difference from the above. And the reason why we're using the sample standard error here is because we're not using a set level of confidence. This is variable. So we need this to actually calculate the different like t-distribution variables in this case. So anyway, it's a small difference, but in this case, we need the sample standard error rather than the standard deviation. And if you're just calculating this for like an exam question and you need to do it quickly, it's fine. It's not going to make a difference because at the end of the day, you're just shoving the data into this function and spitting it out. So something to note. And again, this is just the note. This kind of explains the difference between standard deviation and SEM. Yeah, so we plug it into this function that SIPI has called t interval, and we give it the confidence level that we want, the degrees of freedom, the sample mean, and the sample standard error, and it will spit us out the confidence interval. So that's pretty cool. And there we go, print out this confidence interval. And then for the Gaussian, you can use the same thing, but rather than using the t-distribution, we use the z-distribution in this case, and that's when we have sample size greater than 30. And again, I'll explain why this is relevant in the next video. But again, we're randomly generating integers between 50 and 100. And I'm not really going to go through this full thing, but basically we're doing the same thing as we did for the t, but now we're using the z-distribution, and we're calculating it for two different confidence intervals. So anyway, I just thought I would provide this code in case it was useful for everybody for the exam. But that's all the highlights, at least in general, for confidence intervals, and we'll look at specifically a few more things in homework 3 video. Thanks. Okay, so this is the second part of the confidence interval videos. This is actually the homework 3. So homework 3 was essentially testing the confidence interval test function in Scala, running it for a number of sample sizes, so from 20 to 40, 60, 80, and 100, and then reporting the confidence interval on the number of cases when the true values were inside the confidence interval for both the z-distribution and a t-distribution. So we've covered what a confidence interval is, and now we need to kind of discuss the differences between the z and the t-distribution. So the z-distribution, or the normal, or the Gaussian, or the standard, or they're all the same names, or the names for the same thing. But basically, it is a distribution. If you were to know the population mean and the population standard deviation, then you could and should use the z-distribution. Well, assuming that whatever your population is normally distributed. But many times and normally you will not know those two parameters, so you will have to use samples to estimate the population mean and standard deviation. And this is kind of where the t-distribution comes into play. The t-distribution, or the student's t-distribution, is essentially used in the case when you have a small sample size. And the rule of thumb is that if you have a sample size greater than 30, you can use the z-distribution, or you can reasonably approximate the normal distribution or the z-distribution with a normal, or with a sample set of greater than 30. Excuse me. However, if you don't, If you have a sample size less than 30, then you have to use the t-distribution. And this graphic kind of illustrates why. And just as a refresher, sample size minus 1 is degrees of freedom. So if we look at the t-distribution for different degrees of freedom, we notice that as the degrees of freedom increase, we get closer and closer to the normal distribution, the standard distribution. So essentially, kind of why that's important is because down here for these low sample sizes, we actually have a whole different distribution. We have a lot more area out here towards the tails. We have less area in the middle. So it changes a lot of things for us. So we'll kind of see why this is important when we actually go into the example and really what the differences are. But the t-distribution is a way to work with small sample sizes, and the normal distribution essentially is used when we have large sample sizes, because the t-distribution will be approximately equal to the normal distribution. All right, so let's hop into the actual code. So here is the actual code we were supposed to evaluate. And this is on page 95 of the 75 of the textbook, if you care to go look at it. And this is not exactly the way that it is in the textbook. I made some changes for what we needed to do here in this problem. But essentially, what we're doing is, let's start down here. So I made an object. And this object, all it does is it creates a list of, quote, test values. And this is just a range of sample sizes from 10 all the way to 100. And then we're going to feed that whole list, or every value from that list, into the confidence intervals function. So we're feeding in the confidence interval function. And then we're going to go and we're going to set the population mean and the population standard deviation. We're going to initialize the sample size. So we're passing that in every time. We're going to take the root mean, the square root of the root of the sample size, and then we are going to initialize a random variate generator. It's kind of similar to what we did in Python, for this mu and then some variance. And then we're going to initialize two counts. So we're going to count the number of times that the population mean falls in our z confidence interval, and the amount of times that our population mean falls in our t confidence interval. And then we're going to repeat this test. So for each sample size, we're going to run this test 100 times. So basically what we're doing is we're taking that random variate generator, and we're going to take whatever the sample size is. We're going to go from 0 to the sample size. So we're going to take that many samples, and we're going to save it in a vector y. And then we're going to take that vector y, and we're going to take the mean and the standard deviation and save it as mu bar and sigma bar, or underscore, or whatever you want to call it. And then we're going to use the same formula we talked about before, which is the confidence level, in this case, so z sigma, so z score. And this is actually a built-in function in ScalaTion. So this is taking care of all of the complexities of finding what the confidence interval should be, and then also uses the standard deviation to calculate that numerator in the formula. So I'm assuming, I don't know this for sure, so I haven't checked, but I'm assuming you could pass in another parameter, which would be the confidence interval. If you didn't want 95, 95 is kind of standard, you could pass in another one, and it would just automatically calculate that numerator for you. Anyway, so then we're going to divide by Rm, which is the square root of our sample size again, and we're going to get the interval half width. and then we're going to subtract that from the sample mean and add that to the sample mean, and we're going to get our confidence interval. And then we're going to test, we're going to say, okay, is mu actually in this confidence interval that we just created for the given sample size? And then we're going to do the exact same thing. We're going to do that for T sigma. And the only difference here is that we're substituting really T sigma or Z sigma for T sigma. And that's, again, another function that just uses the the T distribution rather than the Z distribution to get that value. So again, we're just using one of these distributions rather than the Z to find what our confidence value should be, or confidence level value should be. All right, and then we're keeping track of how many of the population means fall in this distribution. Okay, and then I wrote some things to basically just print out these values so we can use it as a CSV to kind of manipulate the data and get some visuals. So now let me open this up and pick out the Excel file that we need. Okay. All right. So here's Excel. And the first thing that we took from the function is we took the basically the count of the number of times the population mean fell in the confidence interval for every value, or every sample size between 10 and 100. And then we plotted it. And as you notice, there's a lot of variability here. Like, ideally, this should be 95 because we have 95% confidence interval. However, when the sample size is small, that doesn't always work out the way that we think, right? So, and this does kind of a bad job of showing this, but if we were to extend this out to, like, say 1,000 or 10,000 sample size, it would get really tight, and it would kind of asymptotically get close to 95. But anyway, so what we do see, though, is as we get closer to 100, there's a lot less variation. So there's a lot of variation here, there's a little bit less variation, and it kind of moves asymptotically to 95 as we get closer to 100. And that would be even more drastic, like I said, if we set it on further out. But another thing I want to point out is that the T distribution is always, or the number of cases that fall in are always greater than the number that fall in the Z distribution. And it may not be obvious why, but if we go back to VS Code and we look at this visual again, you can kind of see that. So what we talked about earlier, so the 95% confidence interval means that 95% of the area has to be in between the two strikes that we make. So if 95% of the area has to be in between the two bounds, and we have less area in the middle and more area out towards the edges, we're going to push, essentially, for the T distribution, that confidence interval is going to widen. So the confidence interval for the T will always be wider than the confidence interval for the Z. And ergo, more cases will fall into a wider interval. Or said another way, it's easier for the population mean to fall in a wider confidence interval. So that's the kind of the logic why. And then we can see in actuality that actually really is the case. And then, there'll be an even more striking visual here in a second. But I also took the start of the confidence interval, the end of the confidence interval for the Z, and the same thing for the T. And I took it for every one of the 100 iterations for every sample size. And then I rearranged it so that it was more usable. So as you can see, there's still those 100 iterations for every sample size going horizontally. And then I took the average for every column, So this would be the average start for the z, average end for the z, average start, end, and then I took the difference to find the range, or the total width of each confidence interval for the z and for the t. And then I culled this bottom column out and put it here. So we have this number of samples, or the sample size, and then the z range and the t range, and then I plotted them. And what you can see is we start out, we have very wide confidence intervals with low sample size, and as sample size increases, the range of the confidence intervals for both the z and the t decrease, and they also get closer together. And that was kind of what we see is as the sample increases, the difference between the z and the t distribution becomes negligible. That's really, and also, as we can see, the size, the width of the t distribution is always larger than the z. So I really think this visual does a really good job of explaining, kind of what the differences are between the t and the z, why it's important, and at least in the context of this problem, I think it pretty much answers what we were trying to solve. So to go back, here's an explanation if you want to refer back to it, but just to kind of recap, the t and the z distribution, you can make confidence intervals with both. The z is typically for large sample sizes, the t is for small, although when the sample size becomes large, they just become approximately equal, and that's why most people just don't really bother with the t, they just use the standard normal, or the z. And we're doing this, and this isn't significant because we can use samples, or large enough samples, to approximate the true mean and the true standard deviation of a population, even if we don't intrinsically know it. Yeah, so I think that's about it for this. Let me know if there's any questions. Thanks again for listening.